Hello everybody, Mr. Hinnon here for this Henstitute video on electric circuits using capacitors. So the biggest thing with a difference between resistors and capacitors has to do with the equation. So if I kind of take a look here, we've got capacitors in series and capacitors in parallel. That's what we're going to look at. When we did resistors, we know that R equals V over I. So as I was kind of going through there, we often use the fact that V equals IR. So when you had them connected in series, what you ended up having is one current going through it, and so they all added up with their voltages. When you had them in parallel, you had one voltage, and their currents kind of combined together. And so the way the equations looked was very important. Same thing's going to happen with capacitors. So let's say that I have two capacitors that are connected in parallel. So these are in parallel with each other. Basically what's going to happen is I know I have current coming out, and some of it's going to go here and some of it's going to go there. Since there is more than one path, what you're going to actually find is that the amount of current or the amount of charge on each plate is going to split up. And so the total charge coming out of the battery is going to equal the charge on each one. But if you add those up, that amount of charge has to come back. So now we're talking about charge rather than current. Well, according to what we learned, C equals Q over V, or in other words, Q would equal C times V. And then I'm going to do one more, that V would equal Q over C. So this is going to be important for us. So as that kind of combines, then what I can do is I can say C1V plus C2V are going to combine. Since they are in parallel, we know they have the same voltage across them. So I can pull out the voltage, and then what you find is parallel capacitors just add up like individuals. This is interesting because this is like resistors in series, but capacitors in parallel will just combine as the sum of those. Well, guess what? In series with each other, our capacitors will combine kind of like resistors in parallel. So we do the opposite here, which is really weird. We know that as charge comes around, it's going to start building up. One of the things you're going to find is the amount of charge that builds up here, it's going to push away the same amount on this one and then push away to kind of come back. So each one of these has to have the same amount of charge. Notice here, they're trying to say that the total has the same charge as the individual ones. That's kind of the idea of the current. There was one current going through it. So when I replace my voltage being split up, I have V1 and V2, and I replace those with Q over C's, what we find is we can factor out the Q's, and you're left with this, and this is how we combine capacitors in series. So it's just the opposite of what's going on with resistors. The next type of circuit that I wanted to look at is what is called an RC circuit up here. This is when we have a resistor and a capacitor combined together. And the cool part is, as the current is coming through here, it's going to go through this resistor, and you're going to get a buildup of this capacitor. And the cool part is when you flip the switch, when you connect it so you get current to flow, you're going to get a buildup of the charge that's going to build up, or you're going to get a buildup of the current, or you're going to get a buildup of the voltage. And so you end up with this relationship that your charge versus time, that it's going to start out here at 0 and it's going to build up to some maximum. It's heading towards that maximum value. And it has to do with the way the resistor is going to kind of control the charge being built up. We can use it this way, or since you know that Q over C is also equal to voltage, you can say that voltage equals the original voltage times 1 minus this e to the negative t over RC. And this little RC, this is sometimes referred to as the time constant. So sometimes you'll see this equation written as V0 times the quantity of 1 minus e to the negative t over tau. where tau is this time constant. So the product of your resistance and your capacitance tells you how much time it's going to take to build up to certain amounts. Now, it doesn't actually tell you how much time it's going to build up to the maximum, because if you think about it, if RC was just equal to your time, then, or the time was equal to RC, then you would have e to the -1, and you still have 1 minus that. So we're going to be talking about this and looking at this relationship. We're going to try to do a lab where we set up an RC circuit and look at how we have this exponential growth that's going on with this. The other one is discharging, that once I have connected it, let's say it's charged up to a certain amount, and then I take out my battery and then I flip the switch to kind of get current to start flowing through this thing. Again, one of the things you're going to see is that you're going to get an exponential decay. This one's actually a better one because most people are familiar with exponential decay. And this is our equation. Notice it looks the same, except it's not 1 minus that. It's just e to the negative t over your time constant. Where would you see an RC circuit? Pacemakers. Pacemakers have what's called a pulse modulator, and that's what's going to eventually cause your little jolt in here. But we need to be able to kind of build up to that little voltage and then drop back down. So we need to have it pulse in there, and that's where that exponential growth and decay is going to come from a pacemaker inside of the heart. That's a little bit on capacitors, whether you put them in their own circuit with series and parallel, or if you're talking about what we call an RC circuit. Hope you enjoyed.